everyone. In this video we're going to do the Chapter 6 Practice Quiz 1. So I've already downloaded the data and have it set up in Jamovi. You'll want to do the same thing. Alright, so this first problem sets up the context for the story. And this is on the first day of class, a statistics instructor gives students a 10-question preliminary exam on picking the correct statistic to assess how much knowledge they have before the class starts. This year, the instructor gave the exact same exam to the students on the last day of class before the exam. He has scores from every student on this test when they took it on the first day of class and when they took it on the last day of class. So which of the following is not an assumption for the related samples t-test? Okay. So normality of distribution of sample means is an assumption. So is the independence assumption. So independence is the idea that within any given condition, the scores and people need to be independent of each other. That's not true between conditions, right? It's the same people measured twice. So the independence is within conditions. So homogeneity of variance is not an assumption for the repeated t. Okay, next we ask you to use software to create a graph of the data. And which of the following best describes the pattern of results? So to create the graph, I'm going to go ahead and run the t-test by clicking on t-test, paired samples t-test. And then I'm going to look at pre-test scores and post-test scores, moving them into the paired variables box. And I am going to look for a descriptive plot to see the graph of our data here. Okay. So if you look over to the right, you can see that pre-test scores were quite a bit lower than post-test scores. So performance seemed to be better on the post-test than on the pre-test. Next, we want to know what is the two-tailed null hypothesis for this study. So our null hypothesis is that there's no difference between the pre-test and the post-test scores. So we're not predicting a direction for a two-tailed test. Our null is just that there is no difference between the scores or they'll be the same. Alright, our next question is use the software to compute the average difference score between the pre-test and post-test. And it asks you to compute the difference as post-test minus the pre-test. So the way Jamovi has this set up is that I entered pre-test minus post-test first, or pre-test first and then post-test. To do it in the other direction, I can just do post-test and then pre-test. And that will put it in that direction. So we want to know the difference score, and so we're going to look for the mean difference by clicking on Additional Statistics Mean Difference. And while I'm here, I'm also going to ask for the confidence interval, effect size, confidence interval around the effect size, and the descriptive statistics, because I'm going to need them all later on. Okay. All right, so looking at our results here, it's asking us to compute the mean difference, and our mean difference is 3.7727. Okay. So 3.77 is the difference between those means. If yours is negative, it's because it's just subtracting in a different direction. And it's okay, it's just that it won't match up exactly with what I'm doing on this video. So it's easier if you do post-test minus pre-test. Next, we're looking for the standard error of the mean of the difference scores. So the standard error of the difference scores is over here next to the mean difference. It's 0.51. So this is the typical distance you would expect between the means if in fact the null hypothesis is true. It's also the standard deviation of the distribution of sample means for all random samples of a size of 44 taken from this population. Okay. So our standard error is 0.51. And then asks for the repeated measures or the related samples t for number 6, and that's provided right here at 7.385 or 7.39. All right, with a t of 7.39, we now need to know the two-tailed p-value. So to get the two-tailed p-value, we're looking right here. The p is less than 0.00001, right? So we have a very small p-value there. If your p-value isn't matching mine, it's probably because the hypothesis isn't correct. Make sure you've selected two-tailed hypothesis over here in your output file, or when you're analyzing the data. All right, next we want to compute the standardized effect size D. And the standardized effect size D is going to be right over here. Our effect size is 1.113, which is a really large effect size. Right? It's a very, very big effect. Next, we want to know the 95% confidence interval around the mean difference. So our mean difference is 3.77. The 95% confidence interval around it is 2.74 with an upper bound of 4.80. So I'm 95% sure that the true mean difference in the population is between 2.74 and 4.80. All right, next we need the 95% confidence interval around the standardized effect size D. And so that's also provided in our output. And our lower bound is 0.73 with an upper bound of 1.49. So we're 95% sure that the confidence interval, or the confidence interval tells us that we're 95% sure that the true effect size is somewhere between 0.73 and 1.49, right? Which means it's somewhere between large and really, really large is our best estimate there. All right, next we have to choose the best APA-style summary statement of the statistical results. So first thing we want to look at here is what is our T? Our T is 7.38 with 43 degrees of freedom, or 7.39 with 43 degrees of freedom. So we're looking for 43 and 7.39, and there are actually only two of them here. Our P's for both are less than 0.001, which is correct. And then the next question is looking at the confidence intervals. Okay? So the confidence interval for the mean difference was 2.74 to 4.80. The D was 1.11, and our confidence interval was from 0.73 to 1.49. So E is the correct one there. All right, next we need to choose the correct summary of the hypothesis test and the effect size. Right. So we know that our mean difference was 3.77 and our standardized effect size was 1.11. So we know that on average scores improved by 3.77 units, right? This was in raw score units, right? We know that they increased by 1.11 standard deviations. Right, so this first one, it says on average scores improved by 3.77 standard deviations. That's not true because it was only a difference of 1.11 standard deviations, which is the effect size D. B, on average scores improved by 3.77, which was a large improvement on a 10-question test, which is true. And the difference is unlikely to be due to sampling error. That is also true because the p-value was less than 0.001. Right, so B is correct. Now in terms of why C and D are not correct, C on average it says scores improved by 1.11. That 1.11 was the effect size D, which is not a correct interpretation of D. And then finally it says on average scores improved by 1.11 standard deviations. That is true, or standard error units. However, we say it's a moderate improvement on a 10-point scale, but it was a large improvement. And also this doesn't make any reference to the hypothesis test where we don't talk about sampling error and the p-value. So B is the best answer there. All right, next, suppose that the instructor finds out that students cheated off one another on the post-test. Which assumption would this violate? This would mean the assumption of independence is violated because each person's score isn't independent of other people's scores. They influence each other's scores by copying off each other. All right, next, which of the following would be called into question based on this methodological flaw in the study? So select everything that would apply. Okay. So if the assumption is violated, you should be concerned about all of your statistical results, right? The p-value, effect size, and confidence intervals may all be affected, and you should be cautious in interpreting results when an assumption is violated. Okay, next, number 15. What is the purpose of null hypothesis testing with continuous p-values? Choose two. All right, so let's go through each one of these. A, determine the probability of getting an outcome as extreme or more extreme than the observed outcome. This is the basic definition of a p-value, that we're going to obtain a t-statistic, and we want to know the probability of getting a t more extreme than the one that we computed, if in fact the null is true. Okay. So A is true. B, describe the size of the difference between two means. That is not true for the p-value. This is what you do with effect sizes. C, compute the probability that the null hypothesis is false. We are never trying to figure out if the null hypothesis is false. What we're checking to see is if our data are compatible with the null. D, convert the difference between two means into standardized units so that the results can be compared with different studies using different measures of the DV. This is what we use standardized effect size for, D. E, obtain a range of plausible values for the population parameter. This is what we do with confidence intervals. Determine how precise the estimates of population parameters are likely to be. This is also what we do with confidence intervals. G, to determine if the theory being tested is false is not the purpose of any statistical analyses. Those are much bigger conclusions that take place within a much larger scientific context. And then finally, E, determine how likely the observed outcome is if the null hypothesis is true, and that is what you're using the continuous p-value for. All right, now 16 and 17, I already answered in 15, so I'm not going to go back over 16 and 17 there. Okay, next for number 18, we have suppose that a researcher computes a t-test with the following results. Now, based on this information, why can't the researcher conclude that the results are not compatible with the null hypothesis and thus the scientific theory is supported? And in this case, the p is less than 0.001, which is strong evidence that the data results are not just due to sampling error, right? But it's possible that there's just something else going on in the study, that there's something wrong with the study which is leading to these results. These aren't just statistical issues, there are also research design and methodological issues. So you have to consider how well the study was done before you can jump ahead and make claims about scientific theories. Number 19. Many scientific studies have found that exercise is beneficial for mental and physical health. Studies have also demonstrated that being outdoors in nature benefits health. A researcher wonders if walking outside in a wooded nature preserve would provide mental health benefits even when it is cold outside and most of the plants have turned brown. To test this, she recruits participants and measures their stress levels using a survey where responses are recorded on a 7-point scale with higher numbers indicating greater stress. Each person reports their stress level and then they're asked to walk for 30 minutes 3 times a week in a local forest preserve. The entire study takes place during the month of January when the temperatures are cold and most plants are brown. At the end of the month, participants again respond to the stress survey. And then we have the APA-style report summarizing these results. We conducted a repeated measures t-test comparing stress levels before walking in the woods to stress levels after walking in the woods 3 times a week for 1 month. Right? So if we look at these two means, we can see that stress levels appear to have gone down, and then we have the t-test to evaluate as well. So the first question is, what is the two-tailed null hypothesis for the study? Two-tailed test is always the scores will be the same. There will be no difference on the pre-test and the post-test. For number 20, choose the best interpretation of the p-value for this study. So our t was 1.26 and it's a two-tailed test. And so the correct interpretation of p-value refers to the probability that I would get a t as extreme or more extreme than 1.26 if in fact the null hypothesis is true. Okay? So that would be A here, the probability of getting a t greater than that or less than that if the null is true. All right. The next one is the best interpretation of the p-value of the study. This is a more verbal description and putting it in the context of the study. And here we have walking in the woods and not walking in the woods, walking in the woods before and after. And we're looking at the p-value of 0.21, which shows us that that difference is likely to be due to sampling error. right? So this data are pretty consistent with the null hypothesis that that difference we're observing between 4.25 and 3.96 is not really a real difference. It seems likely that it's due to sampling error. Right? So we would say here that stress levels did decrease after walking outside, and that reduction may be due to sampling error. And so we're going to withhold judgment on that difference. Right. All right. And I spelled judgment incorrectly. Sorry about that. All right, number 22, fill in the blanks for this interpretation of the standardized effect size. On average, stress scores decrease by an X amount, and this difference suggests that walking in the woods in January is blank. And so let's look at our effect size. Our effect size D is 0.15. If we're using criteria of 0.2, 0.5, and 0.8 for small, medium, and large, that is a small effect. And so also it was a small effect that was probably due to sampling error. And so we could say it decreased by a small amount, and this may not be a practical way to reduce stress levels. Okay, for 23 here, we're looking at an interpretation of the confidence interval around D, the standardized effect size. So we have to go back and look at this. Our confidence interval around D is negative 0.09 to 0.39. So that suggests that it may be a small effect in the opposite direction, where walking outside in January actually leads to increased stress levels, or it might be a small to medium decrease. It's somewhere between those two values, right? So it could be a small increase in stress all the way to maybe a small medium decrease in stress. All right, next, choose the best summary of the scientific literature, and what could we consider here? So first one, these results are consistent with the existing scientific literature on the benefits of exercise and being outdoors. These results were not consistent with that because we found no improvement. Next, these results are not consistent with the existing scientific literature on the benefits of exercise and being outdoors. And then saying that we should replicate the study and figure out why the results are different from the existing literature. And then C, the results are opposite of the existing scientific literature. And this is not the case. Opposite would mean that we found that actually being outside made things worse, right? Exercising outside led to worse scores than not doing that, right? And so the best answer here is B. They're not consistent with the literature, and we should replicate it to find out why. Now this next question is about research methodology, and I realize you probably have not taken a research methods class yet, but there are a couple of things I think that you could probably pick out here even if you haven't taken research methods. Right. So first, let's look at participants were measured twice, and this will increase the amount of variability due to individual differences. Measuring people twice should not increase variability in their scores. B, we don't know if people actually walked outside as they were asked to do. Well, that's a potential problem, right? We don't actually know that. If that's the case, we didn't have a very good manipulation of that independent variable. C, the survey measures stress on a nominal scale. And that is not true. We said that stress is measured on an interval scale. It is likely that the assumption of independence is violated in the study. We have no evidence of that. And then finally, E, it is possible that people might become less stressed for reasons unrelated to walking outdoors, like the end of the holiday season, right? So the fact that we're doing this around January, the holidays are about over, maybe people are just less stressed because of that. All right, so moving on to number 26. There's a great deal of scientific evidence that air pollution is associated with worse physical health, but there's far less research on the impact of air pollution on mental health. To investigate the impact of air pollution on mental health, a researcher asks a sample of people living in Los Angeles, California, to complete a survey assessing their overall psychological well-being on a day that has good air quality. The results of the survey in an interval ratio scale with scores ranging from 1 to 10, with higher scores indicating better mental well-being. The same participants complete the same survey again on a day when the air quality is poor. The results are summarized in the following APA-style statement. All right, so you have all those numbers, and the first one is choosing the best interpretation of the p-value. So our p is less than 0.0001, which is a very low p-value. Right? So what that means is that the probability of getting a t of 5.91 or greater, or a t of negative 5.91 or lower, is very small, less than 0.0001. So if the null hypothesis is true, it's very unlikely I would get a t of 5.91 or more extreme. Right? So A is true. Right? So it is very unlikely that we see this mean difference this large or larger if the null is true and there's really no difference. Right? So the next options, let's go over why they're not right. The next one is B. The probability of obtaining a mean difference this large is less than 0.001 if the null hypothesis is true. So a key here is that it's not just a mean difference this large, it's this large or larger, or this large or more extreme. Okay. Number C, the probability that air quality leads to worse mental health being readings is less than 0.0001. That is not a correct interpretation of the p-value. We're not figuring about the probability of one group being higher than another. It's a probability of getting a t that extreme or more extreme if the null is true. All right, and then finally D, there's a 1% chance that the data are compatible with the null hypothesis, and there's really no difference in mental well-being measures on good and bad air quality days. So the p-value isn't telling us a chance or probability that the data are compatible with the null hypothesis. What we use the p-value for is to determine if the data are compatible with the null. It doesn't work in the reverse. All right, 27. Choose the best summary of the standardized effect size. In this case, the effect size up here was 0.72, which is fairly large, right? And so the effect size is large, and this would suggest that air quality might be an important factor in mental health. B is not correct because it suggests that air quality is not important, all right? Also, it's saying that it might be due to sampling error. We don't learn about sampling error from the effect size. We know that the effect size is not small because it's 0.72, and like 0.8 would be a good cutoff or guideline anyway for large, and same thing with D. Next, choose the best summary of the 95% confidence interval around the effect size. Our confidence interval around the effect size is from medium to large, right? So we're 95% sure that the true effect size in the population is somewhere between medium and large. So the plausible effect size in the population range from medium to large, right? So that would be B. And these both lead to very similar scientific conclusions. Both would suggest that air quality is an important thing to consider with mental health. All right, 29. Choose the best summary of the scientific literature. These results do appear to be consistent with the research that physical health is related to air quality, because we found that the data, our difference, was unlikely to be due to sampling error. Mental health was better on good air quality days than poor air quality days, right? And our effect size was moderate to there. All right. Number 30, we need to interpret our statistics in the context of the research methods used to generate them. So which one of the following statements best summarizes the quality of the research? Again, I know you haven't taken research methods probably, but you should be able to figure out the right answer by reading all of these carefully. A, the research quality is very good as evidenced by the low p-value. Low p-values tell us nothing about the quality of the research. Next, the research quality is very good. The p-value, the effect size, and confidence intervals all tell a similar story. You rarely find that all three sources of info are consistent when the study is done poorly. That is not true. It's very possible you can get consistent results even with a very poorly done study. C, the research quality is fairly poor. It's possible that people's well-being ratings were different on those 2 days for different reasons other than air quality. And that's true, right? That we already talked about, right? It's possible that it's just the holidays being over, which is reducing people's stress. Or maybe the days are getting longer and it's reducing people's stress, whatever the case may be. D, the research quality is fairly poor. They should have not measured the same people twice. You can definitely measure the same people twice, and it does not add variability, nor does it make it difficult to detect effects. So C is the best answer there. All right, our next questions here are asking about which statistic you should use to analyze the data for a study. So remember, this is a really important skill. After you leave this class, you'll get data that you need to analyze, but nobody will tell you which statistic to use. You have to be able to read a research scenario and figure out which statistic is most appropriate. So we have three choices now: a Z for a sample mean, a single sample T, and a related samples T. So let's read this problem. We have a psychologist wants to know if children who can resist temptation make more money later in life. He recruits a group of 20 children and places a marshmallow in front of them. He tells them if they can resist eating the marshmallow for 5 minutes, he will give them another marshmallow. 20 years later, he compares the average individual income of children who are able to resist eating the marshmallow for 5 minutes to the average individual income in the United States. So which statistic should he use to analyze these data? So the key here is they're comparing a population mean to a sample mean. So that means it's either the Z for a sample mean or the single sample T. The next thing you need to know is, do you know the population standard deviation? And we don't. We know the population mean, but not the population standard deviation. So since I do not know the population standard deviation, I'm going to use the single sample T. Okay, I just opened up this flow chart from the appendix in the textbook to help with this as well. So remember, we're comparing sample means. The question is how many? You have one or two. We only have one sample mean in this problem. And then, do we know the population standard deviation? Nope. And so it has to be a single sample T. Number 32, researchers studied the effects of sleep deprivation. 50 students were assigned to 1 night of sleep loss. And the next day, the participants came to the laboratory and were given a series of math problems from which they chose which ones they wanted to complete for money. More difficult problems, if performed correctly, would be rewarded with more money. The next day, these same participants were allowed to get a normal night of sleep. The next day, they came back to the laboratory and were again asked to pick math problems to perform for money. What statistic should be used to compare the difficulty of the chosen math problems across the first and second days? So the first question we have is, are we comparing sample means? Well, the answer is yes. And how many sample means do we have? Now, I realize there are no numbers in this problem, but you can infer from this design that there are measuring people before and after, or another way of like when they had a night of sleep loss and a night without sleep loss. Right? So we have people in two different conditions, with and without sleep loss. So we have two means, and are the means independent of each other? Are these groups independent? And they're not. It's the same people measured twice. So that would be a related T. Number 33, a sample of 25 students participates in a program that's intended to increase their reading comprehension ability. After completing the program, the mean reading comprehension score is 75 with a standard deviation of 9. Is the sample's reading comprehension score higher than the population mean of 72 with a standard deviation of 8? So we are comparing means, and how many sample means do we have? Well, we only have one. We have that one sample mean of 75. So, do we know the population standard deviation? We do. It is 8. So since I know that, it's a Z for a sample mean. Number 34, a market researcher wonders if consumers are influenced by the color of their orange juice. To determine if consumers prefer orange juice that is more orange, she asked shoppers to taste 2 types of orange juice. One juice is the store brand. The other juice is the store brand with food coloring added to make it look more orange. All shoppers tasted both types of juice and rated their sweetness of each juice on a 7-point scale, with higher numbers indicating greater sweetness. Okay. So are we going to compare sample means? The answer is yes here. We have 2. We're measuring people's ratings of the orange juice when it was regular colored and when it was made to appear more orange. So we have two means we're comparing, the regular and the more orange. And are these sample means independent? The answer is no, because it's the same people measured twice, because all shoppers tasted both kinds of juice, right? So everyone's in both conditions. 35. A sample of 35 students was asked to describe the degree to which they agree with the following statement. I'm very happy with my decision to attend this college. They responded using a Likert scale in which 1 is strongly disagree and 7 equals strongly agree. And what statistic should be used to see if that number is different than 4? So do we have a sample mean? Well, we don't yet in this problem, but we'll get one from the sample of 35 people. That 35 people will give us one mean. And then do we know a population standard deviation? We do not, right? This would be a single sample t because we're going to compare that sample mean to the value of theoretical interest, which is the midpoint on the scale, which is a 4. All right, well, I really hope that helps. That's the end of this quiz. There are other practice quizzes for you to try as well. So I encourage you to do that so you can get a good sense of what you know and don't know and what you need a little bit more practice on.